Hello and welcome to this video on solving for a variable in a radical equation. In this video I'm just going to go over one example that has multiple parts of a formula, an equation that involves multiple variables, and we're going to perform certain steps, the same steps that were used in my previous videos on solving a radical equation, or an equation with one radical, or with an equation with two radicals even, to solve for a particular variable, right? To get a particular variable in that equation alone. And then we'll use that solved equation to answer some questions, answer another part about it. Okay, so let me begin by reading off to you my first and only example. And that is the following. So the period of a pendulum. All right, the period of a pendulum is the time it takes to complete one trip back and forth. All right, so if you've never seen a pendulum before, it's just a simple, like, imagine this is a ceiling here, and then there's a string, and then on the end of that string is a big weight, right? And you lift the weight up this way, and and let it go. What happens is it swings, back and forth. All right, the pendulum swings back and forth to be over here at one point, and then over here at another point. All right, and it's just going back and forth and back and forth. A swinging weight on the end of a string, right? And it doesn't have to be a string. I mean, if you've seen like maybe a grandfather clock, there's like a solid metal bar with a big weight on the end of it that's swinging back and forth in a grandfather clock to help time progress, keep track of time progressing. All right, so it's mentioned here the period of a pendulum, again, is the time it takes to complete one trip back and forth. So if you let it swing, pull it back up to, say you pull the weight back up here, let it go, and then it swings, whoop, whoop, back and forth and back. That forth and back one time, right, the time it takes for that to happen is called the period of the pendulum, right? Alright, so the period, which will be represented by a variable capital T, in seconds, right, time in seconds, the period of a pendulum of length L in feet, right? So in my picture here, right, this distance here, the length of the pendulum, that'll be called, capital L for length. And then capital T is, again, just the time it takes to go forth and back once. All right. So the period of a pendulum of length L in feet may be approximated using the following formula, where, T, the period, equals 2 pi. Now remember, pi is about 3.14159 and so on. It's one of those famous irrational numbers. So that's the number pi. All right, so T, the period, equals 2 times pi times, and then here's your radical, the square root of this fraction. The square root of, and then in the fraction inside, the fraction in the radicand, L, right? L is the length divided by 32. Right? All of that is inside the square root. All right, so this gives us a formula here to, again, approximate how long it would take to swing our pendulum of length L back and forth one time. All right, so part A, we're asked to solve the equation for L, right? Right now it's solved for T, right? T is alone. What I would like in part A is to get L alone. All right, so this I'm going to write up some steps here. All right, I'm going to follow the same steps that I followed in a previous video of mine where I was solving an equation containing one radical, right? There is only one radical in this equation. So the first step in that video, as well as in this one, is going to be to isolate the radical. Now you could say the radical term, but this whole thing is one term over here. It's one big product, 2 times with factors of 2 and pi and the square root of L over 32. So I could say that it's isolated, but what I'm going to do is actually get the square root itself alone with nothing out in front. Right? You can leave this out in front if you want, but just for me personally, when there's only one radical, and I do like to get it alone most times. Alright, so let's do that. So I'm going to isolate this radical. That would involve division by 2 pi. Alright, so I'll write the equation again to start. We have t equals this 2 times pi times the square root of L divided by 32. Right. And the first thing I'll do, if I want to get this square root alone, is I'm multiplying by 2 pi. Let's get rid of that by dividing by the 2 and the pi, and do the same thing to the other side. Right. Okay, so now the left side has the period t divided by 2 times pi equals, and the 2 and the pi would be common factors that cancel over here, so now I have just the square root alone, right? The square root of L in the numerator divided by 32. Right, so ignore this blob here, right? This is L in the numerator there. I apologize. It looks like a Z now. I'm sorry. So now that the radical is isolated, I want to undo the radical. Right, once I've isolated the radical, I wish to get rid of that radical symbol. We're going to raise both sides to the index power. Alright. So the index on this radical is 2, right? It's a square root. And the property I'm using here is this one, right? Where if you take the nth root of a radicand, call it a, and raise it to the nth power, as long as this is a real number, right, as long as this is real, right, the nth root of a, so if it's an even root, right, we want a non-negative radicand in order for it to be a real number. Right, hopefully you recall all that. So as long as this is a real number, and I raise the nth root, to an nth power, basically the nth root and nth power like undo one another, and I'm left with just a itself, right? Just the radical itself. All right. So what I'm doing over here, I've isolated this square root. I'm going to take both sides, right, this entire fraction over here, and raise it to the second power. Right? This square root over here to the second power. Raise it to the index. Okay. All right. So what we end up getting here on the left side, remember what it means to square something, raise something to the second power. That means you have this fraction. Okay, so on this left side, we have t over 2 pi times t over 2 pi again. Remember, when you multiply fractions, you just multiply the numerators, multiply the denominators. So the numerator would be t times t, or t squared. And the denominator would be 2 pi times 2 pi, which would be, you have the 2 times 2 in there, so 4, and then pi times pi, or, pi squared. So you have 4 times pi squared, right? But be careful, right? The pi is being squared, not the 4, right? That was the 2 being squared to be 4. Okay. Then on the right side, right, we just undid the radical, right? That square root to the second power there, that's gone. And I'm left with L, divided by 32. Just the radicand. All right. And then you solve the final, the resulting equation after that, right? I've raised both sides to this index power. undid the radical. Now that the radical is gone, I'm just trying to solve for L. Solve the resulting equation, and that'll be that. Okay. Well, to get L alone here, notice the only term with L is on the right side. You have L divided by 32. So I want to get rid of this divided by 32. So that means I'm going to multiply by 32, right? The inverse operation of division, multiplication, right? Do the same thing over here. Multiply by, 32. And really you can think of 32 as 32 over 1 if you want. Right, so on the left side, again, multiplying fractions, you just multiply the numerators. I have 32 times t squared in the numerator, divided by, and then 4 times pi squared in the denominator, equals, and then over here the 32 in the numerator, the 32 in the denominator. The whole point of multiplying by 32 was so that we'd have L alone, right? And there we go. Alright, so here we have L solved for. It's done. Now I'm not completely finished because this fraction is not yet simplified. Alright, remember I don't want a common factor in the numerator and denominator. So look at my numerator, has a factor of 32, which is 4 times 8. Denominator has a factor of 4, so 4 goes into 32, 8. I'd be left with a factor of 8 in the numerator and 1 in the denominator. Alright, so when L is finally solved for, I'm going to switch sides here. We have L equals, I have this fraction where you have 8 times t squared divided by, and then in the denominator I have, pi squared. And there you go, right? L is solved for right here. So that was part A. Right, rewrite the equation so that L is alone instead of T. And remember, L represents the length of the pendulum, right? How long it hangs down. And T represented, the period, how long it takes to swing back and forth once. Great. And I guess we could also check this. I mean, it's just like any equation. If we were to check our solution, let's plug this, if you were to plug this in, 8t squared divided by pi squared, if you were to plug that in for L, you would go through and simplify this, and you'd end up with t equals t. You'd end up with t equals t. If you tried that out, again, you can do that on your own. So this would indeed be a good solution, for L, right? Okay, so same steps as when we solved a radical with an equation with one radical. Right? Isolate the radical and raise both sides to the index as an exponent to undo that radical and solve the resulting equation. And of course, double check your solution. Like I just said it out loud, but you should really plug in this for L back in the original equation and see that you get t equals t. You get a true statement. Okay, now that I have this, we have our original equation now solved for L. I'm going to keep it up on the screen here. Part B of this problem, they're asking me to determine the length of a pendulum whose period is 2 pi seconds. So determine the length. That means that they do not know L. Right? The capital L equals question mark. I don't know the length of the pendulum, but they're giving me one piece of information. They say the pendulum's period is 2 pi seconds. All right. Remember they mentioned earlier that capital T was the period in seconds. So that's when T equals 2 pi. So 2 pi, pi is about 3.14. 2 pi would be double that, about 6.28. So what this is saying is that pendulum that's swinging back and forth, it takes a little over 6 seconds, right, about 6.28 seconds for it to go back and forth one time. we're just asked to determine how long the pendulum would be then. So I go to my, now you could go to either equation. You could go back to the original one and then just solve for L again, but why not just use the one we got here in part A? I have a nice equation that is already solved for L, right? L is already alone. So all I need to do is plug in the value of t. I need to plug in that period to get L. So let's do that. So in this equation we got from part A, I have L equals, right, the length of the pendulum is 8 in the numerator, 8 times, and then t is being replaced by 2 pi. And that's being squared, right? 8 times t squared. And then this is being divided by, right, in the denominator we have pi to the second pi squared. Alright, so let's go through and simplify this. This is 8 times 2 pi times 2 pi, right? 2 pi squared would be 4 pi squared. We saw that earlier actually, right? When you square 2 pi, you have 4 times pi squared. So that's the numerator, and then divided by the pi squared. And then hopefully you see that there is a common factor of pi squared, right? There's a pi squared factor in the denominator, so that'll become 1. And pi squared factor in the numerator, you know, anything divided by itself, anything over itself is 1. So the only factors I'm left with are these factors in the numerator. I have 8 times 4, which is, 32. So L is 32, and that's totally simplified. Well, 32 what? Remember these word problems. You should be answering word problems when you're asked questions or asked to determine things in word problems. You should be answering in complete sentences, and all your numbers should have units attached to them so that they actually have meaning in relation to the problem. Like the 2 pi here has the word seconds afterward. That's the units on that, right? That was the units of the period. Well, this is a length. All right. We're asked to determine the length of this pendulum. So the way I would answer, I mean, L equals 32 is great and everything, but it doesn't answer the question fully. All right. The way I would answer this, if I were given it on a quiz or a test or an exercise set, is I would write out a full sentence. The length of this pendulum, right, that's mentioned, right? The length of this pendulum is, L equals 32, and 32 what? If you went back to the wording of the problem in the beginning, remember they told us that, period was in seconds, the length was in feet, right? So L represents a length in feet. So L equals 32 means that the length of this pendulum is 32 feet. All right, and I'll put this in a box. Right, this is how I would want to see an answer to this question. Full sentence, complete sentence, and all the numbers that are mentioned have units attached to them so that they have meaning. Great. And that's all I got for this video today. Again, the big thing to take away from this are the steps involved, which, again, if you've been watching my videos, you may have noticed that they're the same steps that are involved in solving an equation that involves one radical. Isolate the radical, get the radical alone, raise both sides to the index power, right? Use the index as an exponent to undo the radical, and then you solve the resulting equation, and of course check your solution, double check to see that it's actually a good solution back in the original equation. Great. And as always, I like to add at the end of these, please do the best you can to try to learn the material on your own before you go looking for help. I have found that people who tend to take the time and effort to learn something on their own usually remember that material for longer, and they remember it better, and they're more proud of themselves. So it's good all around. So of course, read the material, read through the author's examples, perhaps even try to work out the solutions to an author's examples before you see how the author did it, and then compare your work with the author's, see if you can learn from some mistakes there. Obviously, work on tons of exercises, practice problems, look up solutions to those whenever they're made available, so you can check yourself, keep track of your progress. And don't just give up on a problem after the first attempt. Don't give up so easily. Very often in mathematics there are several approaches to a problem that'll work out. So if after several attempts or several approaches at a problem, if you're still not getting it, still not understanding, maybe you should go back and read the material again, perhaps even a third time. Because if you've been working on some problems, there's a good chance you have a better grasp as to what the author is asking you for, what the author expects of you. So then reading back through the problem, reading back through the material, you'll have a better idea as to what to look out for in the reading. You'll probably catch some things that you didn't catch the first time. That'll hopefully make things make more sense and make working on the problems that much easier. But if after that, if after several read-throughs of the material, several attempts at problems, if you're still not getting it, still not making sense, well then it's not a sign of weakness whatsoever to go asking for help. That is what other people are there for, to help you. So ask a teacher, a tutor, a friend, someone in your class who you know knows the material well and is willing to help. Look for supplemental materials online. There's loads of it out there. Look for videos online. There's tons of those too. Videos like this one, or plenty of other videos out there that are better than this one, I assure you. They're easy to find. But just keep at it. Stay persistent. Keep practicing. Don't give up. And above all, and I think this is also the hardest thing, is believe in yourself. Stay positive, even during times of struggle and failure. Because it's during those times that you have to push through. It's times of struggle and failure and making mistakes that you can learn the most, right? By figuring out how to fix things and learning from those mistakes, learning from those failures. So, just keep at it, stay persistent, keep practicing, stay positive, maybe even try to have some fun with it, and don't give up. And I just know you'll get it. Thank you very much for watching.